congruency can actually be viewed as a special case of similarity. Okay? If I have two shapes that are similar, we're going to say that one shape is maybe half the size of another shape, or two times as big as another shape, something like that. So we'll have what we call a scale factor. We'll talk about that as we go through here today. With congruent shapes, our scale factor ends up being 1 to 1, okay, which is just a kind of special case scenario for similarity. But now we're talking about what similarity means in general when it's not a 1-to-1 relationship. By our definition right now, we're going to say that similar, whenever you see that word, for us, it's going to mean same shape. Okay, so if we compare similar shapes, if I ask, are these two shapes similar? They both have to be triangles, or they both have to be quadrilaterals, or they both have to be pentagons or something like that, okay? And then they have to have different sizes, okay? If it was the same shape and they were the same size, that's the definition that we talked about for congruency, right? So now we change that component of size, and we're going to then have similarity. All right, so two polygons are similar if their vertices can be paired, so the following two things are true. Okay, first we need corresponding angles to be congruent. Okay, corresponding meaning that they're matching locations, right? In this case, you got angle A and angle E. They correspond, and we're seeing that they are in fact congruent. D and H, G and C, B and F. Okay, so matching parts or matching angles in regards to locations for corresponding, they have to be congruent. Okay, that a lot of times is a fact that a lot of the problems that we are provided, that has already been met. Okay, so usually we will want to be interested in that because every once in a while they'll kind of try to throw us off with providing us shapes that don't have angles that are congruent. But if that's not met, then there's no way we can get to the second component here. So a lot of times that's already being met for. But it is something that is true about two shapes that are similar. Corresponding angles have to be congruent. The second component is where we'll do most of our work, and it says corresponding sides are in proportion. Okay, and that's what we talked about last week for 3 or 4 days with ratios and proportions. Okay, and this is the application of 7.1 in a geometry sense. Okay, basically saying that the lengths have to have the same ratio. So when I compare two side lengths to one another, they have the exact same ratio as any other two side lengths compared to one another, as long as they're corresponding. Okay, so that being said, I can't just take 10 and arbitrarily compare it to any one of these 4 numbers over here. It has to be matched to the corresponding side length. So what would you guys think corresponds to 10? What side? Okay, 5. So you're seeing AD and EH, they are corresponding sides. And the reason they're corresponding sides ultimately comes down to the fact that A was corresponding to E and D corresponded to H. So the segment in between has to correspond as well. But we get 10 compared to 5. All right. If these two shapes are similar, then every other set of corresponding sides should be this ratio. Okay. Now, what would 8 compare to?
4.
8 compares to F4. What would 6 compare to?
3.
3. And 5 compares to 2.5. Okay. Now, none of those ratios are, 10 over 5. I don't see 10 over 5 again in the next 3 ratios, right? But they all simplify to 2 over 1, 2 over 1, 2 over 1, and 2 over 1, right? So because all 4 of those ratios are the same, we do have corresponding sides in proportion to one another. Okay, so we've met criteria 1 where it said angles were congruent, and now we've met criteria 2 where it says corresponding sides are proportional. Now, what we could also do instead of maybe simplifying them, what we have is the idea that if I look at those two, if I don't simplify, what's their cross products? Yep.
40.
40 equals 40, right?
Yeah.
So when 40 equals 40, it tells me that those two things, that's a true proportion, right? So that it allows that equality to kind of stand firm, right? What if I take those two? Okay, what's that cross product?
24.
24 equals
24.
24. So that's a true equality, right? So right now we said those two things are equal, but those two things are equal as well, right? So what's that tell me about that thing and that thing?
Okay, equal.
They're equal as well. And I don't even have to look at them, right? I can use a transitive property there. But if I cross multiply, what's 10 times 3? 30. What's 5 times 6? 30. Okay. And now I could maybe do that cross product. What's 3 times 5? 15. What's 6 and a half, or 6 times 2 and a half? 15, right? So now I've shown basically 10 fifths is equal to 8 fourths, but 8 fourths is equal to 6 thirds. So 6 thirds is equal to 5 over 2.5. And all those things, they can be interrelated, and I compare 10 fifths to 5 over 2.5. I can compare 6 thirds to 10 fifths, and so forth. Does that make sense, everyone? But every single time, they're going to be reduced fully to 2 over 1. All right. Now that 2 over 1, we're going to talk about that in a little bit. That's called our scale factor, which actually tells us then that the figure on the left is 2 times as big as the figure on the right, right?
Yes.
That's that component that says different size. Okay, same shape, different size. And we should be able to determine how different those sizes are. Okay, it's a 2 to 1 relationship here. As we go through and we start talking about similarity and similar polygons, we have some notation stuff that is very similar to what we talked about with congruency statements. You guys remember talking about, if I say triangle ABC is congruent to triangle DEF, we could make arguments about what angle A is congruent to, what B is congruent to, C is congruent to, right? What segment AB is congruent to. You guys remember doing that?
Yeah.
So that's a congruency statement. We have the same thing occurring with similarity statements. Okay, I'm going to come back up to the last picture to write this. But a similarity statement is very similar. You go through, you start at a vertex. What vertex you want to start at?
A.
Okay, A is fine. Where do you want to go from A?
C.
You can't skip a letter.
B.
So I start at A and I got to go to either D or B. So I'm going to go to B,
Oh my god.
and then C, and then D, right?
Sure.
All right, now to maintain correspondence, what do I have to start at over here then?
E.
E, and then go where?
F.
Okay.
G. H. A. G.
So that, we say that these two things are similar by doing this, by putting that symbol in between. Okay. So we read that A, B, C, D is similar to E, F, G, H. And that gives us the two things that need to be met for similarity. It tells us which angles had to be congruent. Angle A would have had to been congruent to what angle over here?
E.
E. What about angle B?
F.
Okay. What about angle C?
G.
And angle D. All right, so that is the exact same approach that we used when we dealt with congruent shapes, right? That's pretty easy. The second component is that sides had to be proportional. Well, let's think about this. What did you compare AB to? That 5 you compared to?
E. F.
Yeah, the 2.5, right? So AB, which are the first two letters here, have to compare to EF. So we have to write that ratio.
And then what? BC over FG.
Okay, so BC is going to be compared to FG.
And CD over GH.
Okay, and what's the last one?
DA over HE.
Okay. And you can flip-flop those. You can call A, B, or BA. You call it EF or FE. Doesn't matter.
Well, if you go BA, would you have to go CB and then DC and then?
Yeah. Just as long as you got that segment. Does that make sense? Now, looking at those guys, what did all the numerators come from?
The small one.
AB is on the small shape?
Oh, the numerator.
Numerator.
The big one.
Yeah. So all the top values and the ratios come from the big figure, right? Okay. And if you remember, when we set up proportions in the story problems, I like to, look at, maybe that proportion like that, just looking at two of these and say, there had to be a link not only between this set of numerators and denominators, but there's also a link between numerators and a link between denominators, right? Okay, I think there's one question in that homework assignment that talks about like the scores at a halftime game, right, or a halftime of a basketball game, and it was like a 3-to-2 ratio. Okay, well that's 3 points for every 2 points, right? Okay, so it's the points that each team had made, but I think there were the Vikings and the Timberwolves.
The Lakers.
Okay, and then they asked us over here. Okay, the Vikings I think led by like 19 points at halftime. And then the Timberwolves would have had X points. Does that make sense? And we see that up top is all scores related to Vikings. On the bottom is all scores related to Timberwolves. Does that make sense?
Yeah.
So when I use that logic over here with similar polygons, my numerators need to have that link. These are all values that come from this figure on the left. The denominators are all values that come from the figure on the right. Does that make sense, everybody? Okay. Now, as we do these, we know that there's 3 properties that exist with proportions that allow you to kind of jockey your values around and get equivalent proportions, right? Or proportions that still provide you the same answer. Like I can flip-flop EF and BC, correct? Okay. But EF and BC being flip-flop, exchanging those means is not the ratio and it's not the proportions that are defined by the definition of similarity. So, whenever we do problems in this class, this is the way I'm going to present, whether you want to view it this way or not, that's your choice. My numerators are always going to come from the same shape. Is that okay? My denominators in are all going to come from the other shape. Okay? But that's going to be the link that I try to maintain every single time that we do one of these problems. Because I think that's just a consistency thing that's going to allow a lot of us to make sure we can develop at least one true proportion that allow us to move through these problems. Now, there are a lot of other proportions that you can make in these problems, and if you feel comfortable doing that, go ahead and do it. But that's how I'm going to link these things. Okay. This slide 4 is exactly what we just wrote down, relating those congruent angles and then corresponding side lengths. Okay. I'm going to kind of skip this one and get to this one where we can actually do some work here. It says, if 2 polygons are similar, then the ratio of the 2 corresponding sides is called a scale factor. Okay? And so in that last one, when we went through and we found everything reduced to 2/1, right? Okay? 2/1 is my scale factor. Okay? A lot of times to start the problem, you're only going to find the scale factor existing inside your picture one time. But once I complete the problem, I find all unknown values, I should be able to replicate that scale factor X amount of times. In this case, if I have 5 unknown or 4 extra unknown sides there, I should be able to find the scale factor exists 4 separate times. Okay. So here we've got, comparing 21 to 35 there. That would be the link of, would you guys agree that VW and DE are corresponding sides, right? And we compare those corresponding sides numerically, get 21/35. Yeah. I like it that way for setting up future problems, but that is when you type the scale factor into Math Excel, that's probably going to count that wrong. They're going to want it to be what? Yeah, they're going to want you to reduce, take a factor of 7 out there, so we get 3/5. Now, we obviously should still know that the 3 came from the smaller figure, right? And the 5 would have come from the bigger figure because 3 is smaller than 5, right? Is that okay with everybody? All right. So there's 2 approaches here that we can go through to find some missing values. Let's say that, just to make things easier, let's say we make this XW 15. Okay. I'm just pulling that number out of thin air. Don't really worry about how I got it. But let's say that's 15. Do we have the ability now to maybe find what X is?
Yeah.
Okay. 15 and X. If these 2 shapes are similar, okay, which that's what we're saying down here. Okay. If we have a scale factor, then there is similarity. If they're similar, every single time I divide corresponding sides, that division went down to 3/5, right? So shouldn't the division of 15 over X also equal 3/5? Yeah. Okay. So what we do is we say 3/5 is the same thing as 15 over x. Does that make sense to everybody? I got a proportion now. Think about my numerators, the 3 and the 15. And that 3 can be kind of thought of maybe as the 21. Maybe if you want to enlarge that again and write it as, instead of 3 over 5, you want to write it as 21 over 35, because maybe it's more obvious here. But would you agree that those two values came from the same shape? The numerators came from the same shape. And the denominators of 35 and x, they came from the same shape as well, right? I'm a person, I like to write my proportions using the unsimplified scale factor. But I'm never going to take 35 times 15. Because I can't really maybe do that in my head. So I'm going to simplify this to 3/5. And now can I do 5 times 15 easier in my head? What's 5 times 15? 75. And then I get 3 times x is 3x. So x has got to be 25 in this situation, right? So this is 25 here. And now think about this. We should know, because this is a smaller shape, right? 15 should have grown to a larger number. Is 25 bigger than 15? Yeah. Okay. Also, when I'm done, 15 compared to 25, what can come out of both those numbers? What divides both of them? 5. Goes in 3 times there and 5 times there, right? Is that my scale factor again? Okay. So when you're done, you can find those values. Okay, now, some of you, that's the way I'm going to do these problems in class in front of you, because I think that opens the door for everybody to be able to have a planned procedure, a planned method for being able to find these missing parts. But some of you might realize this, and it's doing the exact same thing, it's just maybe not as explicit. You might know that, okay, if this is 15, how can I find x? But you know the scale factor is 3 to 5. And what that means to us is that the figure on the left is every side length is 3/5 the size of the side lengths on the right, correct? Okay. Or I could say that the ones on the right, and in the figure A, B, C, D, E, they are 5/3 the size of the ones on the left, correct? Okay. Now, if I say 3/5 of something or 5/3 of something, what does that of mean to us?
Multiplication.
Multiplication.
Yeah.
Okay. So if I take 35 and multiply it by 3/5, it should give me 21. Does that make sense? So if I multiply x by 3/5, it should give me 15. But I don't know what x is, right? So I should be able to reverse the roles. I should be able to take 15 and multiply it by something to get x. What should I multiply 15 here by so that I can get x? Or what would you maybe multiply 21 by so that you get 35?
5/3.
5/3, you multiply by the reciprocal, right? And the idea there is the ratio, the scale factor is 3 over 5. If we're looking at a figure on the left and a figure on the right. If we're looking at a figure on the right and a figure on the left, it's just the reciprocal, it's 5/3. Okay? And if I have a number like 21 or a number like 15, and I want to make it larger through multiplication, you have to multiply by a number that's bigger than 1. Bigger than 1. Okay? So 5/3 is that number that's bigger than 1, right? I've got two choices, 5/3 or 3/5. 5/3 is bigger than 1. Multiply by a number that's between 0 and 1, what's that going to do to something?
Make it small.
Make it smaller. Okay? So I know I need to enlarge this number. My options are 3/5 or 5/3. So multiply that by 5/3, it gives me that number right there. Does that make sense? Okay? So if you're a person that likes to do it that way, by all means do it. But what I want you to understand is that you're doing the same thing. You're doing the same thing and setting up those proportions. Okay? Now, we also know, and this is why I'm going to go off the definition. We know that XW compared to AE, right? And WV compared to ED. That's kind of the proportion that we went through to, VW compared to ED or DE. That was our 3 to 5, right? And this would have been our 15 to, what did we end up that being? Was it 25? Yeah, 15 to 25, okay? So I'm going to write those 15. This was 15 to 25, and this was 21 to 35. Those both reduced to 3/5. But what I want you guys to understand is that it is perfectly legal. Can we, because of what we learned in 7.1, can we flip-flop those two numbers right there? We flip-flop the means. So you could also develop XW compared to WV equal to AE compared to ED. Does that make sense, everybody? But now what I want you to realize is look at those two things right there. Where do both of those come from? What shape do both those come from?
The small one.
They both come from the small one. And now you don't have a scale factor of one shape to the other. Does that make sense? Because when I compare XW, what was XW? 15, and WV is 21. So you get 15 over 21. Okay? Well, what's that reduced to? Careful. 5/7, right? Not the 3/5 that we had prior. Okay. However, what's AE compared to ED? AE is what do we find out? It's 25 compared to ED, which is 35. That still gives me 5/7, right? Okay. However, it's not a scale factor now from one figure to the next. Does that make sense? Okay. You can do that. But the scale factor is comparing figure 1 to figure 2. What is their ratio? And that's not what's happening in that proportion that we set there in red. Okay? So that's why I like, and I will always do this, when we set up these proportions, I will always let my numerators be from one figure and let my denominators all be from the other one, because then that's always going to develop a scale factor from one shape to the next. Okay? See here. Not a lot of work to do here. It's just those two shapes are similar. If I compare the one on the left to the one on the right, I get a 2-to-1 relationship for reducing. If I compare the one on the right to the one on the left in that order, I get a 1-to-2 relationship. Okay? Order is very important because we're going to take that scale factor and decide, am I trying to make, when I try to find unknown values, am I trying to take the current value that I know and increase it, so I multiply by 2, or am I trying to shrink it, so I multiply by half? Does that make sense? So order of comparison is extremely important as we do these. And what I find out to be one of the biggest issues that people have, biggest concerns in kind of processes that they go through that makes them miss questions is that they usually have the reciprocal. Okay, so they're looking at the wrong order of comparison. This is just a notation thing that I don't know if we've talked about it in the past. I don't know if maybe you've seen it using GeoGebra. It'll do this every once in a while. But there are times that we like to be able to reference and use the exact same letter in our pictures. Okay, that represent different vertices. We'll still use like letter A, or still use letter B. We use it multiple times. And similarity is nice because if I use A a lot of times like that A, and I come over here, the way I read that, I call that A prime. Okay. What that allows us to do is ultimately, we're going to make the argument that A and A prime are corresponding angles. Does that make sense? Okay. If you're going to repeat letters like that, it makes sense to repeat them so that you're using them for corresponding parts.
I remember this one.
Okay. So you would never, for instance, I would not call this one A here and then call this one up here A prime, because they don't match in regards to their location. Does that make sense, everyone? Okay. So that's just a little apostrophe above there, and we read it, like I said, A prime. This would be B prime, C prime, and D prime. And if these two shapes are similar, that's kind of how we would write that. So now we could say, well, I'm going to compare AB to A prime, B prime. Does that make sense? I'm going to compare BC to B prime, C prime. This makes it a little bit easier to write and compare parts and to remember parts. You can do that for congruency. You can do that for similarity. You can do it anytime you want to. And you can use A more than twice. You can use it a third time. You put 2 of those marks on it, so it'd be A double prime, A triple prime. You do it 3 times. Does that make sense? Do it as many times you want to put 35 markings up there, do it. Okay? Use A 35 points. If A is the only letter you ever want to use, go ahead and do it. Okay? Kind of silly to do it that way, but That's just a notation thing that we can talk about. Now, you've seen that before?
Yeah.
Okay. All right, so where do we use this? So see a couple examples here. I think we got 2 examples, and we'll be done. It says quadrilateral ABCD is similar to quadrilateral A prime, B prime, C prime, D prime. I'm going to make the argument that A and A prime are congruent sides, or congruent angles. B and B prime congruent angles, C and C prime, and D and D prime. Okay, and we can see that with that similarity statement in the corner, left-hand corner. It says find a scale factor. When you guys find a scale factor, especially when these questions are going to ask you to go further and find missing parts, I wouldn't even set up looking for a scale factor. I would say, okay, what are all the relationships? What are all the parts that I know I'm allowed to compare based off similarity? Do I know that I can compare, what would you compare X to? What side would X correspond to? 21, right? What would you compare 8 to? Y. What would you compare 10 to? Z. And what would you compare then 20 to? 30. Those things should all be equal. Every one of those ratios should be equal if these 2 shapes are similar, right? Which one is purely numerical? Which one is only numbers? No variables. 20 over 30, right? There's my scale factor. Okay. And setting up this extended proportion like this is nice because if all of those are equal, I should be able to take this 20 over 30, which I'm going to reduce to 2/3. Does that make sense why?
Yeah.
Okay. Reduce that to 2/3, and now that 2/3 should be equal to 10 over Z. That 2/3, because 10 over Z is the same thing as 8 over Y, so 2/3 should be equal to 8 over Y. And then 2/3 should also be equal to X over 21. Does that make sense, everybody? Okay. So setting up those 4 ratios and equating them gets you all the little individual proportions you need to set up to solve for X and Y and Z. So I get 2/3 is equal to X over 21. I will get 2/3 is equal to 8 over Y. And I will get 2/3 is equal to 10 over Z. Those are your 3 little individual proportions. This would give you what? 42 is equal to 3x. X becomes 14. This would give you 2y is equal to 24. Y is 12. This would give you 2z is equal to 30. Z is in 15. Is that okay with everyone? And what I want you to understand, all of those numbers right there, which are then those numbers, and those numbers, did they all come from the figure on the left? Smaller figure, right? And then the denominators, 21, y, z, and 3, they all come from the figure on the right. So that's the relationship. Numerators are all the same shape. Denominators come from all the same shape. And then inside one fraction, they are corresponding parts. All right, so I'm going to plug these values in up here. 14, just so we can answer the next question. 14, this is 12, z is 15. I'm going to erase this stuff. So let's find the perimeters of both figures. What would be the perimeter of the figure on the left? What's 10 plus 14? 24 plus 8 would be 32. Plus 20 would be
42. No, 52.
50. Okay, so figure on the left is 52. Let's find this one. Okay, 30 plus 21 is 51. 15 plus 12 is 27. What's 51 plus 27? 78. So I get that comparison of perimeters, right? But what is 52 divided by 78? If I take that on my calculator, there may be better ways of doing this, but if I take 52 divided by 78, what do you get? 2/3. Right? You got to try. You got to do. Like at that point, 6 repeating, right? Which we know is 2/3. Well, what was 2/3? 20 over 30 was the relationship of side lengths, right? Reduce that to 2/3, right? There's my scale factor. So the perimeters are always going to be in the same ratio as your scale factor. Okay? And what is nice is, once I've got all these values, what's 10 compared to 15? What's that reduced to? 2/3. What's 20 divided by 30? 2/3. What's 8 compared to 12? 2/3. What's 14 compared to 21? 2/3. Okay? Well, if I just adding all those up, I just got that 2/3 again, right? Okay? So I'm going to ask you questions. That's a fact. You might want to write down. The ratio of perimeters is exactly the same as the scale factor, or exactly the same as the ratio of two sides, okay, two corresponding sides. I will ask you questions that you cannot draw a picture for. It means it's not feasible. You don't give you enough information. Maybe I tell you you have two pentagons. One has a perimeter of 13. The other one has a perimeter of 26. And I ask you, I don't give you any of the side lengths, but I ask you what's their scale factor. It's 13 and 26. Does that make sense?
Yeah.
Okay. Or if you flip flop and say, here is one side of this figure, this pentagon. Here's a side of the second pentagon. I don't tell you any way of being able to find the other four sides of either, but I ask you what's the ratio of the perimeters. So you can't calculate the perimeters, but you can still figure out what the ratio is. Does that make sense?
Yeah.
Okay. I got one more here.
Okay.
This one here. The first criteria for determining similarity. First criteria for determining similarity is that angles have to be congruent, right?
Yes.
Is angle 30 congruent to angle 30?
Yes.
Right angles congruent.
Yeah.
Okay, so then we know these remaining angles B and E should be congruent as well, right?
Yeah.
So for legs, they're both going to be 60 degrees. So we've met the first idea that corresponding angles are congruent. The second part then, to say that these two figures are similar, is that corresponding sides have to be proportional, right?
Yeah.
So these ratios need to be, all right? So I'm going to take 12, which is that hypotenuse, right?
Yes.
What would be the hypotenuse over here?
9.
9. Okay, across from the right angle, right?
Yeah.
Okay. So those are corresponding parts. They have to be the largest sides, right? Now, what would be the smallest side over here? 6 or 6 radical 3?
6.
6, because it's across from the smallest angle, right? So what would be the smallest angle over here? Smallest side over here?
4.5.
4.5. And then in this figure here, it leaves the 6 radical 3, and over here it leaves the 4.5 radical 3, right?
No.
Okay. Now, these fractions are all ugly, right? And in their current format, you might argue, all they're different because the numbers are different. Well, I'm looking at their quotient. Not just staring at that number is different than 6, or that 9 is different than 4.5. Are they different in the same way? I think the best thing to look at is maybe these two here first.
Cancel out the 3.
Because I can cancel out the radical 3's, right? That's a factor of 1. So if I do that, what am I left with then?
The same thing.
The same thing. So that is true. Those two things are proportional. Let's look at these two. Okay. Are those two equal?
Yeah.
How?
What's 9 divided by 2?
Okay, 9 divided by 2 is 4.5, right?
Yeah.
So you're saying this 12, I think it's a great idea. You're saying that 12 is the same thing as 2 times 6, and that 9 is the same thing as 2 times 4.5. Just like we do with the radical 3's, these 2's are a factor of 1. So now you get this 6 over 4.5 is equal to 6 over 4.5. So those are equal. Another way of doing it was, what do we have, 12 over 9? What's 9 times 6?
24.
Huh?
Oh, no. 52? 54.
54.
Ah.
What's 12 times 4?
No, it's
It's 48, but then 12 times a half is 6. So that doesn't get 54, right? So the cross products here are the same as well. So that's an alternative way of doing it. But we have those two things are equal. If the first two are equal, and the last two are equal,
they have to be.
are those two equal?
Yes.
Yeah, transitive property, right?
Yeah.
So we do end up with, even though the original fractions look really uncomparable or incomparable, they are in fact all proportional to one another. Okay? They will all reduce down to the exact same number. Is that right? So yes, we would say that those are similar, and that's the justification. We've shown that all corresponding angles are congruent and corresponding sides are proportional. Okay? they ask a lot of questions on the intercourse exam dealing with similarities. We want to make sure we feel very comfortable with these ideas. And then it's also going to parlay into the next chapter and the chapter after that. So if we understand it now, it makes those other chapters a little bit easier.